Let's go to the most important part, 3.4. So here we will introduce a very important thing to you. It should be one of the most important things you should know in this course. That is the property table. Okay, we have a lot of property table inside our appendix. Okay, and it's time for me to introduce table A1 to table A17 one by one. Okay, so why do I need to do that? It's because in your homework, the problem would not tell you which table you should use. So I need to tell you what table we should choose in order to reach our goal and find our corresponding quantities. Okay. So note that I will talk about only from A1 to A17. Okay. Table A1 is the molar mass, gas constant, and critical point properties. And inside this table, you can see that we have a lot of substances here. For example, air, ammonia, argon, etc. And we have a formula, molar mass, gas constant, and the critical point properties I've mentioned. Okay. Note for the unit. For this gas constant, some of you may have heard of the ideal gas law, but at that time, the R is called the universal gas constant. But this R, we will call it to be gas constant, okay, having this unit. And this number is material dependent. Okay, for different substances, it has different value, unlike universal gas constant. But in thermodynamics, this R would be more useful than RU, because usually we only get the data about the mass, but not the number of moles. Okay. And for the critical point properties, the volume will be a little bit different. It's m cubed per kilomole. Okay, it's not the specific volume. Okay, I will later explain why. Okay. For the pressure, note that is in megapascal. So if you need to use this critical pressure, then you need to change your unit on your own. Okay. And for table A2, okay, it's called the ideal gas specific heat. Ideal gas specific heat. I will introduce the Cp, Cv in chapter 4. Okay, so no need to bother about this value now. Okay, and let's go to table A3. It is less frequently used. It's the properties of common liquid, solids, and fluids. So some of them are for solids. Okay, a bunch of solids here. And what important is starting from table A4. Okay, so let's see. From table A4 to figure A10, they are all about water. Okay, for A4 and A5, they are for saturated water. Saturated water. Saturated, as I've mentioned, is that it is inside the so-called phase change process. Okay, I've mentioned that temperature table is for the use if you have a given temperature. For the pressure table, if you have a known pressure, then use this table. For table A6, it is for superheated water. That means it is in a vapor state that is not about to condense. Okay, we can get the property here. And for table A7, it is for compressed liquid water. But actually, for compressed liquid, it is very difficult to obtain a property table because almost all of the properties will have the same value. So I will talk about how to treat the properties or find the properties of compressed liquid. Okay. And for table A8, it actually is not frequently used. And for figure A9, it's a TS diagram for water. I will introduce the property S in chapter 7. So just skip this TS diagram at this moment. Okay, and also we have this Mollier diagram. This Mollier diagram is actually what we call the HS diagram. At this time, just forget it. We will jump to table A11. We have a pure substance that is refrigerant 134A. Okay, or we call it in short R134A. This is very common type of refrigerant used in a refrigerator or some HVAC system. And we also have a temperature table and pressure table. Similar to the case for saturated water, this temperature table is used if you have a given temperature. If you have a given pressure, then use the pressure table. And similarly, we have a superheated R134A. And for A14, just forget that, okay, because this pH diagram would not be used in our course. And for figure A15, it is what we call the generalized compressibility chart. Okay, I will introduce it in the very end of this chapter. Okay, well, for table A16, because we do not likely to consider the effects of the atmospheric pressure for different altitude, so you also do not need to know that at this moment. For table A17, is the ideal gas properties of air. You can get the values such as the specific internal energy and other properties. Okay, I will explain the use of those tables in the subsequent chapters, and some of them in this chapter. Okay, so let's see a partial list of table A4. Okay, so you should have seen these two columns because I have shown how to use these two columns in example 1. But how about the remaining one? Okay, we have the specific volume, we have the internal energy, we have the enthalpy, and also entropy. For entropy, you will see it in chapter 7. So forget these 3 columns first. Okay, for specific volume, we will also have 2 quantities. The quantity with F as subscript is what we call the specific volume of saturated liquid, because F is the first letter of the German word representing liquid, okay? And G is another German word meaning vapor. So we have Vg to be the specific volume of saturated vapor. And we also have a definition of VFG. If we have F as well as G as a subscript, it's defined as Vg minus Vf. Vg minus Vf. Similarly, we will have the same use of subscript for internal energy as well as enthalpy. Okay, for internal energy, we also have the internal energy for saturated liquid, okay, internal energy for saturated vapor, and here we have EVAP. This EVAP just means evaporation. UFG, defined as UG minus UF, is the internal energy of vaporization. But usually we would not use this value directly, okay? But it has importance here, so I will explain it in the later sections. Okay, and similarly we will have the enthalpy. But what is enthalpy? Enthalpy is a combinational property. Okay, we have a symbol H to represent it. This small letter H is for specific enthalpy. Okay, for the original enthalpy it should be H. So by definition, the specific enthalpy is equal to the specific internal energy plus pressure times the specific volume. So we'll have this value. Note that this V is small letter v. Okay, this PV, P times V, you should have seen this in the previous chapter. This is what we call the flow work. Okay, the flow work. And you can also check that it actually satisfies the dimensional homogeneity. Okay, if you want to show that, you just treat it as an exercise. For the total enthalpy, total means that we multiply both sides by m. Okay, so the total enthalpy is equal to the total internal energy plus the pressure multiplied the volume. So we have H equal to U plus PV. Okay. So this enthalpy will be used for the thermodynamic analysis for open system, as well as closed system having a constant pressure process. Okay. If you don't understand what I mean, it's fine. I will talk about this gradually in chapter 4 as well as chapter 5. Okay. Okay. So here I need to talk about that. This HFG is the enthalpy of vaporization. Okay. Or you can say that it's a specific latent heat of vaporization. Okay, because the specific latent heat is calculated for the constant pressure heating process or constant pressure cooling process. So here we will use enthalpy to represent this, okay, because we are performing that process in constant pressure manner. Okay. Next, we go to the next subsection 3.4.2. So for saturated liquid and vapor state, for water, you should refer to table A4 and A5. Okay. Do you still remember what the title is? The title of those property table is called saturated water temperature table and the saturated water pressure table. Okay, if it's R1348, then you go to A11 and A12. Okay, so we will have a saturated refrigerant 1348 temperature table and the pressure table respectively. Okay, so the general step is that first of all, we need to recognize whether the pressure or temperature is given. If pressure is given, then you go to pressure table. If the temperature is given, then you just go to temperature table. And the second one is that if you would like to know the specific volume, then you just look at that table and find it. Okay? And this specific volume can help us to determine the state. Okay? Liquid state or vapor state or a mixture. Okay? I will talk about this in the later subsections. Okay? So if you don't understand what I'm talking about, then I can use some example to illustrate how to use those tables. Okay? Okay, so let's go to example 2.